Question 5. Figure 3 shows an arrangement for investigating electromagnetic induction. When the switch is closed, so we start with the switch closed, there is a current in coil X that's going around clockwise when viewed from over here. Circuit Y is also viewed from over here. Explain how Lenz's law predicts the direction of the current when the switch is opened again and when it is closed. Right. So it starts off closed, so there's a constant current travelling through this coil. If there's a constant current flowing through the coil, then there's a constant magnetic field. Now we know the direction of the magnetic field by using the right-hand grip rule. You don't actually require this to answer the question, but I think it makes it a lot easier. So you put your hand down like this, you grip your fingers in the direction that the current is moving, and your thumb points to the North Pole. So we've got two solenoids, we've got two coils of wire, so there's one coil of wire, there's the other coil of wire. So that is behaving like a North Pole, that's behaving like a South Pole therefore. So that's my first coil of wire, so that's circuit X, and that's my second coil of wire, that's circuit Y. Hopefully there we go, they're now on the page. So you've got your coils of wire here, and here, a North Pole there, South Pole there, because the current's going in that clockwise direction when viewed from that position there. Make sure you use your right hand. Now there's no current induced in Y because there's no changing magnetic field. The magnetic field is constant, so nothing happens in Y, there's no EMF induced, and so no current flows. So everything's stationary, everything's still. You've got current flowing here, you've got absolutely nothing happening here. When you open the switch, what's going to happen is this field here is going to collapse. The one that's generated by coil X is going to collapse. And when it collapses, it's like moving this North Pole far away like that. So it's like moving a North Pole away. Now Lenz's law will induce a current, will mean that there's a current induced in this coil here, and it will induce it in such a way as to oppose the change that created it. So if you are effectively moving a North Pole away, then what it's going to want to do is it's going to try and pull that back again. So it's going to try and make a South Pole here and a North Pole here, because it's like pulling this North Pole away, so to pull that North Pole back again, to oppose the change, you need to create a South Pole there. Now you'll notice that those two are the same way around, which means that the current in Y, when you close this, when you open this switch, so when you collapse the field here, the current in Y will travel in exactly the same direction as it does in X. So I think first of all we'll state a little bit about Lenz's law. So Lenz's law states that any induced EMF opposes the change that created it. Okay, that's just common sense. So, when the switch is opened, the field generated by X collapses, so Y tries to bring it back, and a current is induced going clockwise from P. I don't think you need to state that because it clearly states that you were measuring everything from P. So this is the original position with X. If you turn this off, it's like moving that away. So therefore you're going to make a south pole here and a north pole here. So those two orientations are the same, so the currents are going to be travelling the same way round. Okay, now we need to start again. Once everything's settled down, no currents flowing in this coil here. There's no change again, so therefore there will be no induced current in this one here. So it's like having nothing and nothing. If we close the switch, so when the switch is closed, then we recreate our original situation. So right hand grip rule, we get a north pole here and a south pole here. Now, we've gone from nothing to bringing a north pole here. So that's like bringing a bar magnet's north pole close to this one here. Now, Lenz's law means we're going to oppose that again. So to oppose bringing a north pole in, you're going to make a north pole there and you're going to make a south pole there. So when the switch is closed, a current is induced in Y, travelling, and we want the north pole there, south pole there, so your thumb points in the direction of the north pole, so your fingers are now going in the opposite direction. They're going, when viewed from there, they're going anti-clockwise, travelling anti-clockwise. And it's always because it's trying to oppose the change that created it. Okay. And then once this current has established itself again, there'll be no changes in the magnetic field from this, so this will have no change in the flux cutting through it, which means that the current in this coil here will go back down to 0 again. So only if you continually switch this on and off are you actually going to get a continuous or any more induction here. You have to change this side for anything to happen on this side. Determine the flux density BH of the horizontal component of the Earth's magnetic field. Okay, so this is behaving just like a generator. So on your formula sheet here you have the magnetic flux linkage to a generator, or indeed any coil, and here you have the EMF induced of rotating a coil. Well, that's what we're doing, we're rotating a coil here. So the EMF induced is equal to the flux linkage, which is BAN. That's the flux going through any single coil, and that's times by the number of turns that you have. Omega is related to the speed at which we rotate it, and then sine omega t. Now we could work it out for any value along here, but the best way to do it is to work it out for the maximum. And sine omega t, this whole expression here, has a maximum value when sine omega t is equal to 1. That's the biggest value it can take. Sine omega t is equal to 1. So we're going to go epsilon, the induced EMF, is equal to BAN omega sine omega t. So epsilon max is equal to BAN omega, because that is equal to 1. Right, so we need to work out what the epsilon max is. To do that, you get your pencil and you join those two peaks up like so, and you draw along there, and I make that 5.6. Watch the units, microvolts. Okay, so we have 5.6 times 10 to the minus 6 is equal to B, which is what we're trying to find out, times by the area. Right, the mean diameter of the coil is 0.35, so the area of a circle, pi r squared, so we want pi times by 0.35 divided by 2, that's the radius, and we want to square that. And then we want to times by the number of turns, which was written up here somewhere. I'm sure it's 500. Where was it? There, 500 turns. And then we need to times that by omega. Omega is 2 pi f, 2 times by pi times by the frequency, which is 1.5. Okay, so we can calculate all of that now. So this bit first, 0.35, I'll just write down the omega equals 2 pi f. So f's the frequency of rotation, 2 pi is the number of radians in a full circle, and omega is the angular speed in radians per second. So this is revolutions per second, so times by 2 pi radians. Let's bring it to radians per second. 0.35 divided by 2, square that, times by pi, I've done that wrong, times by pi. So that's the area, times by 500 to get the area times by the number of turns, times by 2 pi times by 1.5, and we get 453. Then we need to do 5.6 times 10 to the minus 6, which is from there, divided by our previous answer, and we get B horizontal is equal to, what's it in Tesla, so 1.235 times 10 to the minus 8 Tesla. And we just need to think about sig figs now. That's to 2 sig figs. That's to 2 sig figs, so let's write our answer to 2 sig figs. So it's 1.2 times 10 to the minus 8 to 2 SF. Okay. That's question 5.